My fabulous chemistry faithful, video number 5. We are almost done with nuclear. Today is going to be the first major task of the unit. I know it says here that we're going to identify decay mode and radioactive half-life for radioisotopes, but what we're really going to do is balance these transmutation equations, okay? So, law of conservation of mass, just like we did with balancing equation, will be in play. The total mass and charge, the protons, of the parent nuclei must equal the total mass and charge of the products. Okay. Um, Transmutations do not take into account the mass defects. So there is always that little, there's been that word coming up a little bit where some of the mass that is turned to pure energy is gone, but it's very negligible amount, especially for regions chemistry. Okay. But it's just kind of, that's like a lawyer term, throwing it out there that it's there. We have to know that the science is to stay true to the science, that it's happening. But for our case and purposes, the numbers are going to be exact as far as balancing. All right, so there's a lot to write there. I'm not going to read the whole thing because that's kind of a waste of your time. Parent nuclei, this is the reactant side or the left-hand side of the arrow. So you can see in this little picture, even though it's behind my screen a little bit, that it's beryllium with a mass of 9. It's got 4 protons, right? 4 blue dots. It's got 5 yellow dots in there somewhere, right? And then it's going to turn into a helium with a mass of 4 and 2 protons. So I know that the other missing piece, well, if there's 4 protons in beryllium, there's got to be 4 total protons in the other side. So there's going to be a 2 on the bottom. And then if there's a total mass of 9 and I got 4 on the product side, the other piece needs to be a 5, and it'll all add up. That's really what this unit or this video is all about. Product nuclide is on the right hand side of the arrow, of course. And if these are natural transmutations, there will be the alpha, beta, positron, or neutron, whatever is given off as far as the emissions go. Okay, so there's some properties of these transmutations. Again, alpha decay is the helium nucleus. It's got a total mass of 4. It's got 2 protons, 2 neutrons. And then that other piece has to do with what's going to happen on the other side. And it's like a little clip of some of the transmutation equations we're going to need to be able to balance. Okay, and I'll show you how to do those here in just a second. Beta decay, again, is an electron, so it's got no mass total, but it has a charge of -1. There we go with that -1 in chemistry again. So this is going to come back into play. It's just not going to be the same as when we made an ion and we added a -1 or took away a -1. It's going to be different. We just got to balance on both sides. So we'll see how that plays into effect. Positron is a positive electron. Again, just a little bit more helping you through what's going to actually happen to the parent when one of these things is given off. And then there's neutron capture. When it absorbs a neutron, this is another thing that happens. This is usually how we start fission reactions. Absorbing that neutron breaks it apart, so it's not going to be a natural reaction. So then on to balancing these bad boys, and this is what the really nuts and bolts is. The total left-hand side has to equal the total right-hand side. We can figure out what the right-hand side is by knowing what one side is. So notice that my total protons on the reactant side is 9. So I know that my total protons on the product side has to be 9. So if I just do 9 minus 1, I can get 8. It's pretty easy math to do that, right? I could conversely go backwards and say 8, use the plus sign that's there, 1 equals 9, and now it's how, put an X in for 8 to figure out that it's 8. Or I could go the opposite way and subtract. So I know it's 8. Periodic table tells me 8 protons is oxygen every day. Okay, then I do the same with the top. 14 and 4 is 18. 18 minus 1 is 17. So notice this is an isotope of oxygen. The numbers play out that it's not oxygen with a mass of 16 like on the periodic table. We're going to have a lot of these isotopes for this entire unit. Okay, let me do one more slowly for you, and then we'll pick up the pace. 15 plus 0 is 15. Remember, the 0 on the bottom of the neutron is its charge. It doesn't have any protons. It's just a neutron. So I have 15 total protons. If I subtract 13 from it, I get 2. And then I use 2 protons to tell me who I am. 2 protons is helium. And then I do the same with the top. I have a total mass of 31. 31 minus 27 is 4. Perfect. That's really how this game is played. Okay? I can fill in the missing pieces just by doing some simple math. So now on the next one, things are going to start going a little faster. I got 96 and 6 together. That's 102. I look up 102 on my periodic table and I see it's element NO. And no, I don't know the name of that one. Add up 246 and 12. Quick in my head, I see 258. But there's 4 neutrons. So that's going to have I gotta multiply that 1 up top by the 4. So it's going to be 246 plus 12 is 258 minus 4 is 254. See how we did that? Pretty simple math, right? I just did it in my head, for crying out loud. 27 and 0 is 27, so that's easy. 27 on one side, 27 on the other side. It is going to still be just cobalt, but its mass is going to change. Now its total mass has got to be 60. So this is that neutron capture, where it absorbed that neutron. Okay. Here I got to go backwards. I got 43 minus 1 is 42. Element 42 is MO. And then I have 97 and 1 is 98 on the product side. Subtract out the 1 on the reactant side, and I come back down to 97. So the total mass on the reactant side has to equal the total mass on the product side. The total atomic number, or total protons, the bottom number, on the reactant side has to equal the total protons on the product side. So for the most part, these are easy peasy, simple math. And then we make sure we use the protons to tell me what the letters are. Remember, the atomic number or the number of protons identifies my element. And with that, oh, I thought we were going to be done. We got more. Okay. Whole nother set. So that's okay. 85, right? 83 plus 2 is 85. That is AT. Then I have 209 plus 4, which is 213 minus 1, which is 212. Bam. So I just did that fast right in my head. Here we go. I got 93 times, or plus 0 is 93. Minus 92 gives me a 1. Okay. 1 is hydrogen. And then I have 238 plus 2 times 1. So that's 238 plus 2, which is 240, minus 239 is 1. Boom, this is a hydrogen ion. Boom, because it's got a mass of 1 and 1 proton, so it has no neutrons. It's a helium or a hydrogen ion. Total, this one, ooh, let me go back. This one is the first tricky one because that beta electron over there. So I got 42 total protons on the reactant side. And when I did this originally, remember it was 42 minus whatever that is. Well, it's going to be 42 minus a negative 1. When I subtract a negative 1, now I have to add. And it works out going backwards, right? So if I do a 43 plus a negative 1, I get 42. So when there's that negative 1, that's the only time the math will get even remotely tricky. I use periodic table, look up element 43, it's TC. I have a total mass of 99 on the reactant side. 99 minus 0 is 99. Got that math down? Boom. We're on our way. All right, 19 plus 1 is 20. 20 minus 0 is 20. Perfect. Element number 20 is calcium. I have 41 as a total mass, adding the 40 and the top 1 together. That 41 minus 1 is 40. So this is calcium with a mass of 40. Okay, here we go. Last one is I got 3 on the total for protons on the reactant side. I have 3. 3 minus 1 is 2. Okay, element number 2 is helium. Adding up the top numbers, I have 5 on the product side. 5 minus 2 is 3. This is helium with a mass of 3. Now, we should be done with this simple math, and you can do lots and lots of practice. See ya!